So today we're going to start with one example of relative atomic masses. We explained an example that was given at the bottom of page 45 for chlorine, that it has two isotopes, chlorine 35 and chlorine 37, one of which is 75% abundant and one of which is 25% abundant. And the final value is 35.5. How do we get it? We assume that we are going to take mass of 100 atoms. So we take the mass of first isotope, multiply it with its abundance, add it to the mass of second isotope, multiply it with its abundance, so on and so forth. We'll do the same with the rest of the isotopes. We get the answer. It's for 100 atoms. So divide this by 100, and there you go. You'll get your answer of 35.5. And the units we commonly use are AMU, which are atomic mass units, as atom is very, very small, so the mass is very less. So this is where it is explained that what are atomic mass units. So these are the units which are compared with one mass of one atom of carbon-12, right? What if they come up with a different question in exams, as they had for neon or for magnesium or even for bromine, sulfur, phosphorus? There have been many different examples previously. Let's take the example of neon. This is the table which shows us all three isotopes of neon and their relative abundances in front of them. Are we going to do it? Again, assume you have 100 atoms of it. So the first atom has the mass 20 and the percentage abundance 90.5. So multiply 20 into 90.5 brackets, add it to the next one, 21 with 0.3% abundance. So 21 into 0.3, and then add it into next one, which is 22 with 9.2% abundance. So 22 into 9.2. You'll keep on doing the same no matter how many isotopes are there. There are 10, there are 12, there are 2, there are 8. Whatever happens, keep on going with the same formula and simply divide everything by 100, because in the start we assumed 100 atoms, right? This would give you the mass of only one atom, which you can easily code in atomic mass units. That's about it. Any questions?
No, sir. And sir, will we only be asked about the elements in this table?
No, of course not, because the examples of coded such as phosphorus or magnesium or sulfur are not a part of this table, but they have been a part of past papers.
And Mr. will they give us the percentage of their abundance?
Yeah, these two things, mass of isotope and its percentage, has to be a part of question, because without it, you can't find it. However,
okay,
sometimes they might play a small trick. That is, they give you the overall answer, they give you these values, but let's say they skip one value in between, like this one, and they put it as X and they ask you to find it. Even then, a little bit of reverse method will get you there, right? Because
yes,
this
sir.
is equal to this one, and this can then be solved like a simple mathematical fraction. Take 100 onto the other side, multiply with by this, solve the rest of the two, which you easily can, and subtract them from that value, then divide that value by 21, and you'll get your answer to X. So simply following a few mathematical steps will get you there. So no matter how much they twist this question, they have to give you certain pieces of information to begin with. And from there on forward, the question is a piece of cake if you know this formula. Are we on the same page?
Yes.
Good. Let's move on then. We are supposed to continue with the same chapter, but the last topic, I guess that was 2.5, right after this one, electronic arrangement in atoms. What I'm going to do is that I'm going to explain this topic, but I'm going to correlate it with the static topic of chapter 3 at the same time. So it's like killing two birds with one stone, right? Let's get started. First of all, we already understand the structure of this atom. And by this structure, you have the idea that nucleus is very small, present in the center. It has neutrons, it has protons. We have electrons revolving around the nucleus. They're present in different shells. Now, what this diagram is going to cater is the more information about those shells and those electrons. We have worked enough talking about protons and neutrons used by using mass numbers and proton numbers. Let's talk about electrons. First things first, electrons have been worked upon by many scientists. Rutherford, Niels Bohr are major names. When we talk about these circles that we usually draw around the nucleus, we use the word orbit or we use the word shell. Let me tell you, scientists were inspired by the universe, so they started using the word orbit because they considered the model of atom much similar to the model of solar system. So they considered just like Earth revolves around the solar system, maybe electrons revolve around the nucleus in this similar pattern. So they started calling these circles as orbits. But that's not the word we recommend. What we recommend is that you use the word either shells, which is a general term, but a more appropriate term would be energy levels. Why do we use this word? Let's come to discussing that by taking this diagram as an example. Now this diagram gives us three shells. The one closest to the nucleus, then there is second one, and third one is finally farthest from the nucleus. Let's start with the first one. The first one has the lowest energy. It's called lowest energy level or first level. It's pretty simple. Only 2 electrons can fit in this level because it's very small, closest to the nucleus. Second one is second energy level. 8 electrons can fit into this level. Third energy level, 8 electrons can fit to give a stable arrangement. However, it can contain a maximum of 18 electrons. This maximum of 18 electrons is not a part of your course. Why am I telling you this? I'm telling you this because if they use bigger numbers in papers, you shouldn't get confused with it. Now, what do we mean by this line? Stable arrangement. Let me tell you, when we use the phrase stable arrangement for the number of electrons in a shell, that means we can start filling the next one. By that I mean, as soon as you have 2 electrons, you cannot put any more in the first shell. So let's say you have 1 electron over here and 1 electron over here. Let's use a different symbol. Let's say you have 1 electron over here and 1 over here. You cannot put any more electrons into the first shell. It's filled. Now you should start filling second shell. Now second shell consists of 8 electrons. So let's draw those 8 as crosses. Let's not consider any dots electrons in there. As soon as you have 8 electrons in the second shell, it is filled. Now you cannot fill anymore. When we talk about third energy level, as soon as we fill it with 8 electrons, it's not the maximum that it can hold, but it becomes stable at this arrangement. What that means is that we can start filling up the fourth shell without even completing the third one first. And after putting 8 electrons into fourth shell, it would also become stable and we can start filling the fifth one. Although fourth shell can contain a maximum of more electrons than we have previously considered for first, second, and third. This might come as a little confusing for you. So we need to go with Niels Bohr's theory in order to understand all the steps one by one. Number one, electrons are in orbit around the central nucleus of an atom. Understandable, we have discussed it before. Electron orbits are called either shells or energy levels, and they have different energies. Remember, the ones that are closest to the nucleus have lower energies, and in the similar way, it says in the next point that shells which are farther from the nucleus have high energy. I would rather say to use the word farther instead of further, all right, with an A. Now, the shells are filled starting with the one lowest energy level or closest to the nucleus. It can only hold 2 electrons, a maximum. The second and subsequent shells, by subsequent we mean a phoenix shell, which includes third, fourth, fifth, sixth, so on and so forth, can hold 8 electrons to give a stable arrangement, which means we can start filling the next one then. So as soon as you have 8 in second shell, you start filling the third one. As soon as you have 8 in the third shell, you can start filling the fourth one. And the manner goes on. But let me tell you, third shell can hold a maximum of 18 electrons, while fourth shell and every subsequent shell can hold a maximum of 32 electrons. So they may hold more. And sometimes in paper, you may get a higher number. Do not get confused by it. How are you supposed to deal with that higher number? Let me explain that on the next page. Okay, moving on to the next page. We have a big, huge table on the next page, which tells us the name of elements, their symbol, their atomic numbers, and number of electrons they have in every shell. Take a look. Hydrogen is the smallest atom in the world just because it has 1 electron. So that has to be put in the first shell, and that's about it. Helium has 2 electrons in its first shell, and there you go. The first shell is completely filled. For any more electrons, like lithium has 3, the next electron goes in the second shell. Then we start filling the second shell. Take a look, beryllium has 2 electrons in second shell, boron has 3, carbon has 4, nitrogen has 5, oxygen has 6, chlorine has 7, neon finally has 8 electrons, and there we go. Second shell is also filled. Now we cannot put any more electrons in first or second shell, so we started putting electrons in third shell. So sodium has 1 electron, magnesium has 2, aluminum has 3, silicon 4, phosphorus 5, sulfur 6. Chlorine 7, argon has finally 8 electrons in the third shell. Now third shell is stable. I wouldn't say it is completely filled, but I would say it's stable, so that we started filling in the fourth shell. Potassium has 1 electron in fourth shell, and calcium has 2 electrons in fourth shell. Either you can put in the dots, or you can write them in numbers. Writing them in numbers is a pretty simple method. We keep writing the numbers for shells, the electrons they hold, and we either keep putting in commas, like we did in the table, like this, for potassium, or you can even put full stops in between. Both the methods are acceptable and have been used in past papers. What do these numbers mean? The first number means the number of electrons in the first shell, second means second shell, third means third shell, fourth means fourth shell. If there are commas and numbers after, this means there are the number of electrons in fifth, sixth, seventh shell. So I think this is pretty easy to read. We call it electronic configuration or electronic arrangement. This electronic configuration or arrangement tells us a lot about an element, because it's going to give us the complete electronic picture. As soon as we get the complete electronic picture, we can always relate it with the periodic table. Before I explain this picture, let me relate it with chapter number 3. For that, I use the phrase in the start of this lesson that I'm going to kill 2 birds with 1 stone. Now, as soon as we move on to chapter number 3, we know that we need to work with the periodic table. So when we talk about periodic table, the elements are arranged in the order of increasing proton number. The vertical columns with similar properties are known as groups. The horizontal rows are called periods. But it's not just what groups and periods are about. What we do say at this point is that groups represent